How's it going, everyone? So in this first video, we're going to take a little bit of time and set up all of the theory and understanding that we need for Chapter 8 in order to work problems involving dry friction, which is all that we're really going to be covering in this chapter, kind of due to our timing constraints since we're moving towards the end of the semester. So I'd like you to consider a scenario like this. It's hard to see, but I actually have this coffee can resting on a stack of books and actually a cardboard box, really just to try to do a little bit of a visual aid to make a point. So you look at this coffee can and it's in equilibrium, right? It has weight associated with it. It's symmetrical, so we know that we could actually describe its weight by a single force acting at the center of gravity, and it's not moving, so we know that the resultant force on it is zero. So what that must mean is that the weight of this object, which is pointing in the downward direction towards the center of the Earth, is counterbalanced or opposed by the normal force that this block, or the kind of setup, exerts on the coffee can. So let me ask you a question. What if I push the can ever so slightly? And believe it or not, it might not look like it, but I am pushing it now. I've exerted an additional force on there. And that is a horizontal force, of course. And we know that the normal force, by definition, is always going to be perpendicular to the surfaces of interaction. So question for you, why isn't this coffee can moving? Clearly, there's a resultant force acting upon it in this case. There's a little bit of a push to the right. So what that means is there must be some push to the left. And we know from our daily lives that that force that's tending to oppose that applied force that I'm pushing in the horizontal direction is known as friction. And that's what we're going to talk about in this section today. So when we think about a statics course and we talk about any force, including the frictional force, we're interested in describing a lot of kind of common tendencies of those forces. Namely, how large are they? What are their magnitudes? What are their direction? And where are they applied? And so on. So that's what we're really going to be setting up in this initial learning module as I disassemble my visual aid there. And you see whatever ads were served up to me there, hopefully not anything too embarrassing. So when you think about friction, our book formally defines it as force that acts parallel to the contact surface between two objects. And its whole goal is to it's not a goal, it's just a tendency, is to prevent the relative motion of one body to the other. And your book uses two terms to kind of define the nature of that motion. They refer to it as either slipping or sliding. And we know that in terms of, so that's where kind of the direction, it's going to be parallel to the 2 points of contact surfaces. But if you think about it, if I have box, kind of the example that I did before, the coffee can and then the surface that it's resting on, and I'm pushing it to the right, if all I knew was that the frictional force was parallel to the two contact surfaces, it could go this way or it could go this way. How do I determine its actual direction or its sense? And we know that empirically it acts in a direction that opposes relative motion. So in that case, when I was pushing the can this way, the frictional force by definition would go that way, and it would be aligned on a line of action that's parallel to the interaction of the two surfaces, rather than perpendicular. So why does this actual interaction occur? Well, it's beyond the scope of studying in a statics class, because usually in a statics class, you're interested in kind of dealing in the aggregate and not the microscopic level, but it's based upon the actual interactions at the molecular level of the various materials that compose the two bodies. And that's why if you look in your textbooks, it's probably not surprising to see, or just kind of go based upon your daily life experiences, that depending on the particular material that each of those bodies is composed in, the kind of level of the frictional force, and we'll define what we mean by that formula here in a minute, will vary. So it's kind of, if you take a chemical engineering class, maybe you'll learn some things about van der Waals forces and so on, but just know that it's the kind of tendency or the ability of one surface to oppose motion relative to another is dependent upon actually the type of material that each is made of. So when you think about the types of problems that are worked in this text, one thing that I wanted to bring up is looking at this free body diagram that we have drawn here. We have a horizontal force applied P. We have the weight of the body, and the two things, the point of what is being shown in this middle diagram here is that this force is distributed across the entire surface. However, we know that from a modeling point of view, any distributed force we can replace by a single equivalent concentrated force using the techniques that we've used up until now. In addition, it's important to understand that in order for all of this to be valid, you have to be pulling this block at a height that's not too high such that it actually won't tip. So that's what all of this relatively small h, large A means. In order for friction to be kind of the dominating force and not actually tipping of the block, you don't want to be pulling it at the top, you want to be pulling it at the middle for all this to be valid. So in terms of a background, if you've ever taken a physics class or after this class, this is one graph that you're going to have to know. And this is something that we're going to have on the final exam as well. And basically what it shows is if I were to vary the magnitude of this force P, or the amount that I'm actually trying to push that block to induce motion in the horizontal direction, what actual frictional force is being applied. So going back, and it's kind of hard to see now, but probably because I've tilted my camera, hopefully you can see this. But if I push a little bit, and this thing is in equilibrium, it probably makes sense to you that the amount of frictional force that's opposing the relative motion isn't equal to the maximum amount of opposition that these two surfaces can provide. Naturally, it's only if it stays in equilibrium, we know that the frictional force only pushes back however much I push to the right. And that's exactly what this is showing here, is as I vary, notice on the x-axis here, the quantity is P, and that is the magnitude of the applied force. So what this is basically saying is as you apply a little bit of applied force in the horizontal direction, the frictional force is just going to be equal in magnitude. And of course, we know it's opposite in direction based upon those empirical quantities that we described earlier. So up until a point, that frictional force can provide whatever force is necessary to counterbalance the applied force in the horizontal direction. That's why F is equal to P here. But we know that eventually, regardless of the scenario, we can push hard enough and that can, or that body, whatever it may be, will start to slip. So there must be some point where kind of frictional force, in order to keep it static, isn't sufficient anymore. And that point on the graph is kind of indicated by where we transition from this linear line and we have a discontinuity and we actually go down. So this is the maximum static frictional force. And I'm sure that many of you remember back from your physics class, that the way you can compute what the maximum static frictional force is to take this parameter mu sub s and then multiply by the normal force. So if we think back to the scenario that we had on the previous slide, if this body had some weight, its normal force would be equal in magnitude. And in that case, what it's saying is that the maximum amount of frictional force that can be provided based upon the interaction of those two surfaces is going to be proportional to the normal force, where this constant of proportionality is mu sub s. Now think about what mu sub s must be. We just kind of emphasized earlier that really what dictates how much friction can exist between two bodies is the nature of the actual materials that they're composed of. So mu sub s is actually denoted as the coefficient of static friction. It says between two forces here. Let me edit that. Of course, it's not between two forces. It is between two surfaces, and it really depends upon the type of material that each surface is made of. A key point that you want to know, that's the maximum value that can exist. But once an applied force exceeds that maximum value and this thing actually goes into motion, what happens is the frictional force will drop, and it's given in that case, again, proportional to the normal force, but the constant of proportionality, mu sub k, is now the coefficient of kinetic friction. And you always want to know, just kind of a thing you can ask someone to see if they've had any exposure to this beforehand, is ask them, hey, what is a larger quantity, the coefficient of static friction or the coefficient of kinetic friction? And as we see in this inequality here, the coefficient of static friction is always going to be larger because after the applied force exceeds the maximum static friction force, frictional force drops and this thing goes into motion. One interesting thing to note is if you were to compute this as mu sub k times n, that would imply that it's constant, but we see that for very large values of p, it goes away from a constant and actually starts to drop off. If you push this thing hard enough, certain aerodynamic effects start to go into play and the frictional force is even farther reduced. But the key point that I want you to realize, and we'll emphasize this through some examples very quickly in the next slide deck, is that the frictional force is not always, if a body's not moving, the frictional force is not always mu sub s times n. It's whatever is necessary based upon the force that's applied in order to keep that thing in static equilibrium. So hopefully that made sense and served as a good introduction there. One thing that I should have added that's emphasized pretty well in your book is here we're particularly dealing with what is known as dry friction. Another name for that is Coulomb friction. And what that means is that there's no lubricant applied between the two surfaces. So the coefficient of friction is going to be dictated totally or solely by the actual material properties of the two bodies in this case. So I will see you all in the next video.